Section: Introduction. In this section, we discuss recent advancements in large language models, LLMs, that can handle very long contexts, enabling applications like code analysis and document summarization. However, processing these lengthy sequences demands significant computational power and memory due to the complexity of the self-attention mechanism. To tackle these issues, various methods have been developed to lower memory usage and speed up processing. For instance, flash attention offers an efficient way to implement global attention on GPUs, significantly cutting down memory and runtime. Ring attention takes this further by spreading the computation across multiple devices, allowing for better scalability. Other distributed strategies, such as tensor and data parallelism, have also been proposed to optimize computation across machines. Some research has shown that we can simplify the attention matrix using sparse attention methods, which reduce complexity from quadratic to linear or log linear. Techniques like sliding window attention and kernel-based approximations have been introduced for efficient long sequence processing. Additionally, memory-efficient methods, such as key-value cache compression and low-rank approximations, trade off some precision for lower memory requirements. We present star attention, a new algorithm designed for efficient long-context inference in LLMs. This method recognizes that LLM inference typically involves two stages. First, we encode the prompt and store key-value vectors in a cache, and second, we generate tokens by attending to this cache. In many long-context scenarios, the input consists of a lengthy context followed by a short query and answer. The information needed to answer the query is often found in small sections of the context, allowing context tokens to focus on nearby tokens while query tokens attend to all previous tokens. Star attention employs a two-phase approach. In the first phase, we divide the context into contiguous blocks and distribute them across different hosts, with each host receiving a copy of the first block, known as the anchor block. Each host computes self-attention for its assigned blocks without needing to communicate with others, which reduces the attention complexity from quadratic to linear. In the second phase, the query is replicated across all hosts, where it attends to the KV cache. The results are then aggregated at a designated host, which updates its KV cache. This method allows the context length to scale linearly with the number of hosts and works seamlessly with most transformer-based LLMs without requiring additional fine-tuning. We evaluate star attention on Llama 3.1-8b and Llama 3.1-70b across various long-context benchmarks. Our results show that star attention can achieve up to 11 times faster inference while maintaining high accuracy. Furthermore, it can be combined with other optimization methods, such as flash attention, for even greater speed improvements. In summary, star attention operates in two phases. First, we encode the context by dividing it into blocks and processing them with local attention, and second, we handle the query and generate tokens using global attention. Each phase is designed to enhance efficiency while ensuring that we maintain the quality of the outputs. Section Summary. In this section, we introduce star attention, a novel algorithm designed for efficient long-context inference in large language models, LLMs, by dividing the context into blocks and utilizing a two-phase approach for processing. This method significantly reduces computational complexity from quadratic to linear, enabling faster inference while maintaining high accuracy, and can be combined with other optimization techniques for further enhancements. Section: Phase 2. Query encoding and token generation. In this section, we describe Phase 2, where we use global attention to encode the query and create output tokens. We utilize a distributed softmax algorithm that allows us to avoid transferring key-value (KV) cache between hosts. A specific host, referred to as the query host, manages this process. The query is sent to all hosts and is converted into a sequence, where the length of the query and the dimension of the attention head are defined. Each host calculates its local attention output for the query using its own key-value pairs. Along with the local attention output, each host also keeps track of the sum of the exponents from its local softmax operation. The query host collects the local attention outputs and the sums of exponents from all hosts. We then compute the global softmax denominator by summing all local exponents. This global sum is used to combine the local attentions, ensuring that the global attention scores are properly normalized across all hosts. This method only requires the transfer of a single scalar and a vector per token, which minimizes data transfer between hosts. After calculating the global attention output, the query host generates the next token and updates its KV cache with the new token's key and value vectors. This process is repeated for each token generated. Our two-phase approach, first encoding local context and then globally encoding the query, significantly enhances inference speed while maintaining accuracy close to that of global attention. We evaluate star attention on various llama-based models with sequence lengths from 16,000 to 1 million tokens using the ruler and Bobby-Long benchmarks. We start by comparing the accuracy and speed of star attention against the baseline, ring attention. We also explore how different block sizes affect accuracy, highlighting the trade-off between accuracy and speed. Additionally, we analyze specific cases where star attention performs well or faces challenges by looking at different ruler task categories. For our models, we benchmark both the base and instruct versions of the Llama 3.18b model, which can handle context lengths up to 128,000 tokens. We also assess two gradient.ai models that extend the context to 1 million tokens. To test the scalability of our method, we include the LLM 3.1 to 70b instruct model, noting that larger language models achieve even greater speedups with star attention on long context tasks. In our baseline comparison, we contrast star attention with ring attention, which computes global block-wise attention by having each host share its KV cache in a ring pattern. We implement star attention using the Hugging Face Transformers library, conducting all experiments on A100 GPS with B-float16 precision. For evaluation, we use the ruler benchmark, which includes 13 tasks across 4 domains: needle in a haystack, retrieval, multi-hop tracing, aggregation, and question answering. We also report results on the Bobby-Long benchmark, which involves tasks requiring multiple supporting facts for accurate answers. Our results show that star attention achieves similar accuracy to full global attention, with only a slight accuracy drop of 0 to 3% while providing up to 5 times faster inference. This indicates that star attention effectively retains the model's ability to retrieve relevant information, even with a smaller context window. For larger models like LLM 3.1 to 70b instruct, we observe even greater speedups while maintaining comparable accuracy. We further extend our analysis to the Bobby-Long benchmark using various LLM 3.1 models. Here, we find that star attention maintains similar accuracy to full global attention, with a 0 to 3% accuracy drop across tasks up to 128,000 tokens. However, we notice some inconsistencies with the LLM 3.18b base model on the Bobby-Long benchmark, particularly a significant improvement at 16,000 tokens but a sharp decline at 128,000 tokens. These variations likely arise from the benchmark's specific requirements for generating answers, which can be challenging for base models not optimized for instruction following tasks. More details on these findings are available in the appendix. Section Summary. In this section, we describe Phase 2 of our method, where global attention encodes the query and generates output tokens using a distributed softmax algorithm, minimizing data transfer between hosts. We evaluate the performance of star attention against baseline methods, demonstrating significant speedups while maintaining accuracy across various models and benchmarks. Section: Trade-off between accuracy and speed. In this section, we examine the balance between accuracy and speed. We find that larger block sizes during context encoding, with a sequence length of 128,000 tokens, lead to better accuracy with star attention. This pattern holds true across all sequence lengths we tested. Our experiments suggest that a block size of about 1/4 of the total sequence length offers the best trade-off between accuracy and speed. For sequences longer than 128,000 tokens, we set the block size to 32,000 tokens to enhance speed, accepting some loss in accuracy. For larger models like LLM A3.1 to 70B instruct, we reduce the block size to 16,000 tokens. The choice of block size ultimately depends on the user's preference for accuracy versus speed. As we increase the block size, star attention's performance gets closer to that of full global attention, giving users flexibility in managing computational efficiency and accuracy. More details about our experimental setup can be found in the appendix. Next, we analyze the strengths and weaknesses of star attention using various task categories within Ruler, which includes 5 main categories: single NIA, multi-NIA, multi-hop tracing, aggregation, and question answering, QA. Our results for the LLM A3.1 to 8B instruct model at a sequence length of 32,000 tokens show consistent trends across all tested lengths. Notably, star attention performs almost as well as global attention in single NIA tasks. However, in more complex tasks like multi-NIA and QA, we observe a slight drop in performance, with reductions between 1.6% to 4.9% for multi-NIA and 0.9% to 6.8% for QA. Despite these declines, star attention maintains an overall accuracy of 95 to 100% compared to global attention. For tasks like multi-hop tracing and aggregation, which require a deep understanding of context, star attention faces challenges. Multi-hop tracing is particularly difficult because it needs the model to share information across multiple hops, but star attention lacks interblock communication, relying instead on global attention between the query and separate key-value caches in each block. This limitation leads to a significant drop in performance compared to global attention. In contrast, aggregation tasks, which involve extracting common and frequent words, show significant performance gains across all sequence lengths due to star attention's chunk-based context division, which enhances summarization capabilities. In our ablation study, we focus on the needle in a haystack (NIA) task, which tests the model's ability to find a small piece of relevant information within a large context. We explore 3 variations from the Ruler benchmark: single NIA, multi-key NIA, and multi-query NIA. We also investigate the role of anchor blocks in Phase 1, which help star attention mimic global attention behavior. Anchor blocks manage attention spikes at the start of each context block. We consider 2 hypotheses for their effectiveness. Either the model develops a bias towards the anchor block's position, or the content of the anchor block is crucial for performance. To test these, we vary both the position and content of the anchor block in our experiments with the LLM A3.1 to 8B instruct model. For the position of the anchor block, we keep its content fixed and test 3 scenarios: randomly sampling position IDs, using position IDs from the previous block, and fixing them to the first block. Our findings indicate that changing the anchor block's position has little effect on accuracy. When examining the content of the anchor block, we fix its position and vary its content across several configurations. Our results show that the content significantly affects performance, with the original content yielding the best results. This suggests that for effective global attention in Phase 2, local context blocks need to attend to anchor blocks that reflect what the model would see during global attention. Finally, we test using the previous block as the anchor block and find that this configuration results in lower accuracy compared to using the first block. In summary, we conclude that while the position of the anchor block is not critical, its content is essential for achieving optimal performance. Section Summary. In this section, we explore the trade-off between accuracy and speed in star attention by varying block sizes, finding that larger blocks improve accuracy but may slow down performance. An optimal block size is about 1/4 of the sequence length. We also analyze the effectiveness of anchor blocks, concluding that while their position has minimal impact, their content is crucial for maintaining performance, particularly in approximating global attention. Section: Size of anchor block. In this section, we analyze how changing the size of the anchor block affects our model's accuracy while keeping the block size fixed at 32K for a sequence length of 128K. We find that increasing the anchor block size improves accuracy, with the best results occurring when the anchor block size matches the context block size. Although we observe that attention spikes mainly happen in the first few tokens, reducing the number of tokens in the anchor block significantly decreases performance. This indicates that a larger anchor block is essential for maintaining accuracy, even though attention spikes are concentrated at the start of the sequence. This suggests that the anchor block's effectiveness may involve factors beyond just managing attention. Our findings are consistent across different model types and sequence lengths. We will explore why the anchor block size should equal the context block size in future research.